Hello everyone, my name is Yudong Luo. This video is a brief summarization of our paper, Learning Selective Communication for Multi-Agent Pathfinding. Learning communication among agents while reinforcement learning or imitation learning has been shown to be an effective way to solve multi-agent pathfinding. Usually, a graph is formed by treating each agent in the environment as a node, and connecting neighboring agents if they are inside the field of view of each other. For example, DHC combines graph convolution with reinforcement learning. The other two use graph neural network with imitation learning to learn communication. However, we can see that most existing communication-based multi-agent pathfinding solvers, including the three papers mentioned before, focus on broadcast communication. However, it is impractical for large-scale problem. On one hand, it causes huge communication overhead. On the other hand, it leads to redundant information and could impair the communication. So in this work, we propose to learn a succinct communication protocol, which allows agents to actively select relevant and influential neighbors for communication. Our method is called decision causal communication. Briefly, agent A communicates with its neighbor B only when the presence of B causes the policy adjustment on A. The motivation is that most learning-based multi-agent pathfinding methods guide reinforcement learning with global or local optimum paths. To diminish communication cost, an agent should follow guided policy as often as possible without communication. Otherwise, it communicates with those neighbors who will individually affect its policy. Our method can be divided into two stages. At the first stage, the agent uses local decision module to check if its policy is adjusted due to some neighbors. To do so, the agent constructs several local observations by masking out one of the neighbors and check if its policy is adjusted. And the second stage, the agent uses request-reply mechanism to communicate with those neighbors who will adjust its policy individually. In our implementation, the messages are updated at both request and reply round. Here we show several advantages of our method. First, can DCC benefit the performance? We compare our method with Primal and DHC in the same environment setting, and DCC outperforms these two counterparts. Second, can DCC select relevant neighbors? One may think that the nearest neighbors are most relevant. We show that it is not really the case. Here we build a baseline model, very similar to DCC, but only communicates with the nearest two neighbors. Results show that in agent-dense environments, communicating with the nearest neighbors is not the best choice. Third, can DCC reduce communication overhead? Here we compare the communication frequency with the baseline model. A request-reply pair is counted as one-time communication. Our method requires much less communication frequency compared with only communicating with two nearest neighbors. And thanks for listening. For more details, please check our paper.